Hello, everyone, and welcome to today's webinar on spectroscopic ellipsometry. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Carrie Hermans, one of our scientists at EAG, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Peter de Box, Senior Specialist at EAG Laboratories.
Thank you, Rena, and I'd like to welcome everyone to today's presentation in our series of Smart Chart webinars. The subject today is spectroscopic ellipsometry, or SE for short. Let me briefly introduce myself. My name is Peter de Box. I received MSc and PhD degrees in chemistry from Utrecht University in the Netherlands. I did research on analytical instrumentation at the Royal Philips Research Labs before joining the Material Science Labs, which at the time was also part of Philips. I have over 30 years experience in a wide variety of analytical techniques, including chromatography, ellipsometry, and X-ray spectrometry. I'll begin the webinar with an introduction to EAG, then follow with a detailed description of our Smart Chart. The acronym stands for Spectroscopy and Microscopy Analysis Resolution Tool. After the introductory slides, I will continue the webinar starting with the fundamentals of ellipsometry, followed by real-world examples illustrating the applicability of the technique to a wide variety of examples. I will summarize by stating the strengths and limitations of the technique. First, a brief introduction to EAG Eurofins. Eurofins EAG is a European company with locations around the world. The orange dots here in the US, Europe, and Asia are the different lab locations, and the blue dots are some sales locations we have in the UK, Australia, and Asia. The lab in the Netherlands, where I work, has been added to the Eurofins EAG group in 2018. One of the advantages that we have with all these locations is that people can get local access to several hundred highly educated scientists and engineers working in the labs around the world. Our range of equipment and diversity of expertise allows us to offer comprehensive materials analysis serving many industries. Also, if we don't have the technique in your specific location, we will get the samples right to the lab, to the right lab for you. Another advantage of having these things in different locations is that if anything happens in one location, we can switch samples between sites and still meet your turnaround times. I should also note here that we have an organization-wide quality system, either ISO 17025 or 9001, for many techniques, and we're both registered and certified. We test instrument performance weekly and have external audits by both accreditation bodies and clients. Because we have a wide choice of instruments and specialists that can operate them, we are in a position to service a broad range of industries across the globe, from pharmaceuticals to aerospace, from medical devices to semiconductor and semiconductor equipment, as you can see in this slide. Because ellipsometry is a thin layer characterization technique, we cater to a selection of these industries, as indicated by the orange frames in this slide. As this series of webinars is named after the Smart Chart, let's have a closer look. The chart, colloquially called the bubble chart, has been used within EAG for a long time, and some of you might have come across it earlier. The Smart Chart captures the broad technical capabilities of EAG in one graphical representation, so that strengths and limitations can be easily compared. The x-axis on the plot shows the lateral resolution or spot size of the technique. On the y-axis is the detection range. either in atoms per cubic centimeter on the left-hand side or in weight fraction from percentages to ppts on the right-hand side. Along the bottom are our imaging techniques that provide dimensional analysis or other surface properties. Detection limits, that is the y-axis that I just showed, don't apply here. On the right side, hand side, are so-called bulk analysis techniques, as samples are consumed in the measurement. Here it is the spot size that is not relevant. Inside the box are techniques that generally operate as top-down sampling techniques at target surfaces. For these techniques, both analytical spot size and detection limit are relevant to determine which is the most appropriate technique for a given analysis. Finally, you'll notice that the bubbles are color-coded. Blue indicates a technique that does strictly elemental analysis. Orange means the technique can provide molecular or chemical state information, often along with quantitative or semi-quantitative elemental analysis. In this seminar, we're going to be talking about ellipsometry, which is colored purple in the plot, because the technique stands out from most others in the sense that it does not provide compositional information, neither elemental nor molecular. Optical constants and layer thicknesses are the main analysis results. Compositional information needs to come from other sources. As you can see in the chart, ellipsometry can measure large to moderately small areas. Also, volume concentration detection limits are average, but it should be noted that surface concentrations of the order of 0.1 monolayer can be readily detected. One last general information slide before turning to today's subject. This figure shows the approximate depth of analysis of various techniques that sample at surfaces, and it demonstrates an important factor to consider when discussing these top-down analysis techniques, of which ellipsometry is one. It is seen that the depth of analysis can vary strongly depending on the characteristics of the technique. The information depth of ellipsometry depends on the type of sample being analyzed, ranging from several tens of nanometers for metals to 10 to 20 micrometers for transparent materials. Let me stress that the information provided in this figure and in the smart chart illustrates that there is no single technique suitable for all analytical problems. We need to tailor our choice of tools to what we're trying to measure, and in many cases, combining different techniques that provide different information will help solve some of the more complex analytical problems that we are confronted with in our daily work. So let's move to the topic of today's seminar, spectroscopic ellipsometry. Spectroscopic ellipsometry is a thin film technique that has spread over the past decades from basic research in physical sciences to a large number of industries, such as semiconductor, data storage solutions, flat panel displays, communication, biosensor, and optical coating surfaces, as shown here in the slide. The increase in use of ellipsometry is explained by increased dependence on thin films in many areas. The broad range of industries utilizing ellipsometry can be explained by the flexibility of ellipsometry to measure most material types, such as dielectrics, semiconductors, metals, superconductors, organics, biological coatings, and composite materials, as is seen here. Also, as a result of technological advances, especially the huge increase in computing power, ellipsometry has evolved from a slow manual technique to the fast, fully automated technique it is today, thereby also contributing to its proliferation. In the slide, I have listed a number of applications taken from literature. Next to the industry, you also see the application for which it is used, and in the last column on the slide, in the second column on the slide and in the last column, you see the kind of materials that were analyzed. At the bottom, I also mention in situ ellipsometry. I will not cover this topic in this presentation, but it should be noted that ellipsometry is often used to follow deposition processes in real time. It is used for process control in thin film processes such as CVD, sputtering, or evaporation by measuring the thickness of the film during growth. At our laboratory in the Netherlands, we have a JA Woollum M2000 variable angle spectroscopic ellipsometer. The M2000 is an instrument with a vertical stage, and either a fixed stage or a translation stage can be mounted. The instrument can be used for measurements of reflection and transmission, ellipsometric data, and also for polarized transmission and reflection intensity. It has a wavelength range from 191 to 1689 nanometers. The minimum spot size of the present instrument is 200 micrometers, but for most applications we use a 2 millimeter beam. We can handle sample sizes ranging from several millimeters to 300 millimeter wafers. You can see a picture of the instrument here at the top left of the slide. At the top left, top right, sorry for that. Top right of the slide, you see the same instrument, but now equipped with a heat cell that can be temperature programmed between ambient and roughly 300 degrees C, which allows the acquisition of real-time data as a function of temperature. As the heat cell is a sealed enclosure, we can also change the gas composition during the real-time measurements. In front of the instrument, you can see the gas mixing system that allows us to make these different gases. And finally, although we rarely use it, I must admit, we also have a liquid cell enabling measurements in liquid, mainly water environments. To understand the fundamentals underlying ellipsometric measurements, we need to look into the properties of light. Light can be described as a traveling electromagnetic wave. For the purpose of ellipsometry, it is sufficient to consider only the electric field. The electric field of this transfer wave is always orthogonal to the propagation direction. Therefore, the electric field of a wave traveling along the z direction can be described by its x and y components. In ellipsometry, we are interested in the polarization state of the light. The polarization state is defined by the shape that the electric field, resulting from combination of these x and y components, traces out at any point along the z direction. Several types of ellipsometric polarization can be distinguished. When the orthogonal x and y components are in phase with each other, a linearly polarized wave results, as shown here at the top left of the slide. If the orthogonal waves have a phase difference of 90 degrees and are of equal amplitude, the light is circularly polarized, as you can see at the top right. If the combined x and y components have arbitrary phase relations and amplitudes, the light is elliptically polarized, as is illustrated here at the bottom. This is the most common form. Note that both a line and a circle are special forms of an ellipse. And last but not least, ellipsometry derives its name from this elliptical polarization. A natural way to define the directions of the x and y component of the electric field is relative to the plane of incidence. The plane of incidence is the plane perpendicular to the surface of the sample that contains the incident and the reflected light, as shown in the plot below. The two components of the electric field are now defined as one parallel to the plane of incidence, denoted as P, and the other perpendicular, denoted as S from the German senkrecht, which of course means perpendicular. It follows from the continuity conditions of electric and magnetic fields across the optical interfaces that the P and S components reflect differently. The incident light interacts with the sample and reflects from it. The interaction of the light with the sample causes a polarization change in the light, generally from linear to elliptical polarization, as shown here in the figure below. We start with linear, we end up with elliptical. This change is measured by analyzing the light reflected from the sample. The polarization change is represented as an amplitude, psi, times psi defined here, and a phase difference, delta, as defined in this equation. Because ellipsometry measures a ratio instead of pure intensities, it is not affected by intensity stabilities of the light source or atmospheric absorption, as are normal transmission and reflection measurements. To recap, in the measurements, we have the following sequence. First, linear polarized light is made to irradiate the sample. After reflection, the light is elliptically polarized because S and P components reflect differently. Then the time-varying intensity created by a rotating analyzer is measured and Fourier analyzed. And in the final step, psi and delta are calculated from the Fourier coefficients and orientations of other optical elements in the system. We can now have a closer look at the instrument I showed earlier. Although there are several different optical configurations possible for an ellipsometer, and ours actually different from the polarizer rotating analyzer configuration I just discussed, we can still recognize some of the more important components of the ellipsometer. From right to left, we first have the source. The source has two lamps to cover the entire wavelength range, from 191 to 1689 nanometers, a deuterium lamp for the UV region, and a quartz halogen lamp for the visible and near-infrared part of the spectrum. In the middle, you see the sample stage that is mounted on a goniometer with an optional XY translation stage, which is not shown in the picture. Left and right from the sample are the polarizer and the analyzer optics that we just talked about. And at the far left is the detector, which is an arrow-based monochromator. Now, ellipsometry does not measure sample properties directly. It measures psi and delta, as just explained. But these psi and delta are functions of these properties. Now, to extract useful information about thin films, a model is constructed that describes the optical properties of the sample. Then the unknown optical properties and the thicknesses are fit using an iterative nonlinear regression algorithm to obtain a best match fit between the theoretical response and the experimentally measured psi and delta. I will explain that again in the next slide. So data analysis of ellipsometric data requires some expertise and experience. This is due to a number of choices that you need to make in the analysis. First, a model needs to be built. That means that the substrate and the layers on top of the substrate need to be defined. Then for every layer, the optical constants or the dispersion function, that is the function describing the dependency of the optical constants on wavelength, need to be selected. In our software, we have a choice of more than 20 different dispersion relations. Next, initial estimates or starting value for the parameters to be fit need to be chosen. Subsequently, the fit is executed using a non-linear Levenberg-Marquardt algorithm, as shown in the slide. The quality metric for the fit is the so-called MSE, or mean squared error of differences between measured and calculated values. For a good fit, the MSE needs to be minimized. After obtaining the results, they have to be evaluated. One of the problems of nonlinear fitting algorithms is that the iterative fit can end up in a local minimum, as shown here, where we want to end up in the global minimum, as shown there. And although the J.A. Woollum software has provisions for finding the global minimum, local minimum fits can never be completely excluded. Also, part of the results evaluation is checking the physical viability of the fitted results. For instance, the extinction coefficient should not be allowed to become negative, and the refractive index should decrease with increasing wavelength when there are no absorptions close by. Real-life samples are never ideal, in the sense that surfaces and interfaces are never mathematically flat, and layers are rarely completely homogeneous. A number of these non-idealities can be incorporated into the fit. Surface and interface roughness, for instance, are modeled using an effective medium approximation. In the case of surface roughness, this means that an additional layer is added on top. This, as you can see here in the picture, this layer is a model mixture consisting of 50% of the underlying layer material and 50% void. The optical constants of the layer are determined by the mixture model, and the thickness is fitted from the measurement data. Thickness uniformity can also be modeled by assuming a range of thicknesses in the analysis, as shown in the second part of the slide. Concentration gradients perpendicular to the surface of the samples are modeled as a stack of layers with increasing or decreasing values of the optical constants. You should note, of course, that incorporating sample non-idealities in the analysis always leads to additional fit parameters and hence a more complicated fit. Now let's move on to some real-life samples of ellipsometric measurements. In selecting the examples, I try to include a broad variety of different analytical questions and different materials, thereby illustrating the wide range of ellipsometry. We will start with a simple example of a transparent film. This example is simple because the extinction coefficient is 0 over the entire wavelength range and hence does not need to be fitted from the data. In this example, we have a thin layer of thermal oxide on a silicon substrate. You can see the measured psi and delta on the left-hand side of the slide. The model we have used to fit the data is shown in the upper left-hand corner. You can see that we have introduced a thin layer of 1 nanometer thickness between the oxide and the silicon to obtain a better fit. The results of the fitted optical constants can be seen at the right. It is seen that the extinction coefficient in green is indeed 0 over the entire wavelength range. The refractive index starts high at low wavelength and decreases towards the higher wavelength, which corresponds to a physically correct form of the dispersion function. A more complex example of a transparent film on a substrate is presented in the next example. Here we have a 3 micron thick polyimide film. The measured psi and delta are show a densely spaced fringe pattern. This is caused by the interference from light reflected from the upper surface with light reflected from the interface of the layer with the substrate, as is illustrated here in this figure. The thicker the layer, the denser the spacings of the interference fringes. This polyimide layer has another property that causes data analysis to be more complicated, as it is often observed with polymer layers that are highly aligned or mechanically stressed. The optical properties of the film are not the same in all directions. These materials are optically anisotropic or birefringent. The simplest case, as encountered in the present example, are the so-called uniaxial anisotropic materials. These materials have one optical axis, and the refractive index depends on the relative orientation of the electric field direction to the optical axis. If the field oscillates perpendicular to the optical axis, that means that the propagation direction is parallel to it, the ordinary index N0 applies. If the electric field oscillates parallel parallel to the optical axis, propagation direction perpendicular, we find the extraordinary index, NE for extraordinary. For all other relative orientations and hence angles of incidence, the refractive index is generally a mixture of N0 and NE and thus has a value between these two. Let's now turn to a couple of examples in which the measured thin film does show absorption. The first example is a 100 nanometer metallic silver film on silicon. The metallic film is so thick that light cannot penetrate to the metal-silicon interface. That is to say, silver is to all intents and purposes opaque to the light at the wavelength we are using in the experiments here. That implies that we cannot measure the thickness from experiment. This holds for most metallic films thicker than around 20 nanometers. For transparent layers, as we have seen in the previous example, the information depth of ellipsometry is much larger, reaching 10 to 20 micrometers. In this case, we will have to settle for the determination of the optical constants only. The measured psi and delta are again shown on the left-hand side of the slide. Using a generic B-spline dispersion model for the silver that incorporates absorption, we can now fit for the optical constants. The result is shown on the slide as well in the lower right corner. As expected, the absorption of the film is high, with K values between 1 and 4 over the measured wavelength range. Our second example of an absorbing film is an organic film on glass. We again use the B-spline function to model the dispersion relation. The model is shown at the top left. As you can see from the measured data on the left, there is observable interference. That is to say, this film is not so thick that the light cannot penetrate to the interface between the layer and the glass. This means that we can fit for the value of the layer thickness, which turns out to be around 53 micrometers, as is shown here. The result of the fitting can be seen again on the right side of the slide, where we see a rather complex behavior of the extinction coefficient as a function of wavelength. This type of behavior is normal for absorbing polymer films. Let's now turn our attention to samples that do not consist of a single layer, but are rather a stack of layers on a substrate. The stack I have chosen as an example consists of P dot, and that is 3,4-ethylene dioxythiophene, on indium tin oxide on glass. The P dot ITO combination is often encountered in organic LEDs and photovoltaics. Both materials are conductive and will hence show absorption. To tackle these more complex problems, we need to take a stepwise approach. Solving for the entire stack in one run requires too many unknowns to be solved simultaneously and is generally not feasible. What we do is we measure the glass substrate first and fit for the optical constants as shown on the left-hand side here. The optical constants of the glass substrate are then held fixed in the next step where the optical constants and the thickness of the indium tin oxide are determined. Obviously, to do this, we need a sample of indium tin oxide on glass only, so we need an additional sample. The results are shown, as I just showed, here on the right-hand side. We see that the indium tin oxide, the ITO, is slightly absorbing in the visible part of the spectrum. Also note that surface roughness was included to improve the quality of the fit. In this slide, we have copied the results of fitting the ITO on glass from the previous slide here on the left-hand side. We can now proceed to fitting the entire stack. In doing this, we will not only fix the optical constants of the glass, but also the optical constants of the indium tin oxide and its sigmas. The results of fitting the complete stack are shown here on the right-hand side. We see that the P dot layer not only exhibits absorption in this wavelength range, K is different from 0, but also is birefringent, as we have seen earlier in the example of the polyamide layer on the substrate. Our next example will be mapping of thin film properties. In acquiring these data, we use a programmable translation state to access the different positions on the sample that we want to include in the mapping. In this example, we determine the thickness homogeneity of a carbon film deposited on a silicon substrate. As it proved difficult to find a unique solution for both the thickness and the optical constants of the absorbing film, we measured one point of the film, as shown here on the left, with a different technique, X-ray refractivity or XRR, to determine the thickness. Fixing the thickness at the XRR measured value in the subsequent analysis of the ellipsometric data, we could then determine the optical constants of the film. And these results are shown here on the right-hand side. Now, knowing the optical constants, we proceeded by measuring a predetermined grid of points on the sample. For these points, the thickness was determined using the optical constants of the carbon film determined previously. The results are shown in the contour plot at the bottom of the slide. It can be seen from the plot that the thickness is not very homogeneous. The measured thickness ranges from around 30 to around 60 nanometers, depending on the position on the silicon wafer. In this example, again an example of measuring its function as position, we measured how well the wet etching of a silicon on insulator sample could be controlled. On the left-hand side, you see the model we used for the silicon on insulator sample. The fit to the data is shown on the right-hand side. At the bottom left, you see a contour plot of the silicon thickness both before the etching. On the right-hand side is the contour plot of the silicon thickness after the etching. It is readily seen that the boundary between the silicon oxide and the remaining silicon is a jagged line instead of a nice straight line as intended. So there was some work to do for the process engineers here. Our next example had a similar analytical question. Here the question was whether depositing in a fluoropolymer film depended on the substrate it was deposited on. Two samples were measured. On the left-hand side, you see the fluoropolymer deposit on silicon directly. On the right-hand side, the fluoropolymer layer is not deposited directly onto the silicon, but on an intermediate 500 nanometer thermal oxide. You can see the results of the analysis in the two contour plots at the bottom. It emerged that the thickness of the film is slightly larger at around 9 nanometers when deposited directly on silicon as compared to the thickness of around 7 nanometers when deposited on the thermal oxide. In the next two examples, I would like to show you a comparison of ellipsometric results with analysis results of other thin film techniques. In this first example, we compare the thickness measurement of a contaminated area on a surface. The three techniques used were ellipsometry, atomic force microscopy or AFM, and X-ray photoelectron spectroscopy XPS. Ellipsometry and XPS were measured on the contaminated area, whereas AFM was measured the height increase at the edge of the contaminated area. Comparing the results, we see that ellipsometry determines a thickness of 15.33 nanometers, while the thickness determined using AFM and XPS were 14.9 and 13 nanometers respectively. For these very thin films, we always see discrepancies between the different techniques, and that often leads to lively discussions among the specialists. However, given the uncertainty in the determination of thickness for the various techniques, we feel that the agreement is satisfactory. Our second example, and a comparison of ellipsometry with other techniques, concerns the characterization of thin nitride layers on silicon. In this slide, you see the comparison between ellipsometry and again XPS. In the ellipsometry analysis, the nitride layer was modeled as an oxide nitride using a Bruggeman effects medium approximation, as we discussed earlier. Also, a native oxide film on top of the silicon was taken into account. The XPS data were analyzed assuming no mixing between the nitride and the oxide. The total thickness is somewhat higher at 6.1 nanometers, as determined with XPS, when we compare that to the 5.2 that was determined with ellipsometry. Therefore, we used a third technique, and that technique was transmission electron microscopy. It was performed on the same sample, of course. You can see the TEM image at the top right. Thicknesses of the different layers were determined from the contrast in the image, leading to a native oxide thickness of 1.1 nanometer and oxynitride thickness of 3.8 nanometers. It is seen that the total thickness determined using TEM nicely coincides with the thickness determined by ellipsometry, given the error margins on both measurements. As you can see here, the total thickness remained somewhat higher. The total thickness determined by XPS remains somewhat higher than the thickness determined by the other two techniques, which we don't completely understand, of course. So far, we have presented examples and case studies in which the thickness and optical constants of thin films were determined. The bulk of the work we do with ellipsometry at EAG is this type of analysis. However, other thin film properties can also be extracted from ellipsometric measurements, some of which cannot be determined in any other way because of the minute amounts of material present in these films. Some of these properties are the surface roughness that we already discussed, the optical band gap, the thermal expansion of the thin film, adsorption and desorption behavior on surfaces, and the porosity of the thin film. Let's look into the determination of the optical band gap first. The procedure is as follows. We first perform ellipsometric measurements in the usual way. From the measured extinction coefficient, we calculate the absorption coefficient. Then we plot the square root of the absorption coefficient multiplied by the photon energy versus the energy. Such a plot is called a tau plot after its originator. As is shown on the bottom right, extrapolating the linear range of the plot to the energy axis yields the energy of the optical band gap at the intersection. This optical band gap value can carry important information. For instance, for diamond-like carbon layers, the optical band gap is related to the sp2-sp3 ratio, and this ratio determines the hardness of the DLC, which is a distinctive property of the layer. The second example of the determination of non-optical properties of thin layers is shown here. We can measure the coefficient of thermal expansion by collecting ellipsometric data as a function of temperature using our programmable heat cell. By fitting the optical constants and the thickness for all temperatures measured, we can derive the coefficient of thermal expansion by plotting the thickness as a function of temperature and calculating the slope of the line. This has been done in the examples shown on the slide. Here, the CTA of a thin layer of an acrylate mixture, as used in synthetic materials for lenses, was measured both while heating and while cooling down. In this next example, we have measured adsorption and desorption of water on a modified silicon oxide surface at different relative humidities. We use the heat cell again as an enclosure and our mixing system to control the gas composition. The measurements shown here were carried out at room temperature, but it is of course also possible to do the same experiments at any other temperature between ambient and 300 C by programming the sample temperature. In the figure, you see the effect of switching between different relative humidities. It is seen that the thickness of the adsorbed layer nicely follows the relative humidity. And note that an absorption isotherm could be constructed from the measured data. Also note that the ellipsometric measurement is fast enough to follow the fast changes in absorbed amounts that are observed when changing the relative humidity. Also, the high sensitivity of ellipsometry is nicely illustrated. Given that the thickness of 1 nanometer at 80% relative humidity roughly corresponds to 3 monolayers of adsorbed water, it is seen that small fractions of a monolayer can indeed be measured using this technique. My last example of properties other than optical that can be measured using ellipsometric measurements relates to thin film porosometry. The total porosity or the void fraction of a layer can be determined again by modeling the layer using a Brugman effective medium model that we discussed earlier. You mix the material and the void, and in the void fraction is of course the porosity. In this example, the layer is modeled as a mixture of the underlying glass because this is a glass. The fitted void fraction was equal to the porosity, as I just said. As can be seen in the example of the glass that is corroded at the surface, In principle, the pore size distribution can also be determined by measuring an absorption isotherm, or by several, as shown in this example here at the bottom, taken from literature. Earlier, I showed you this slide where I argued that ellipsometry can be used in many industries and is very versatile with respect to the different materials such as dielectrics, semiconductors, metal organics, and composite materials that can be measured. Here I have highlighted some of the examples that we just discussed. Obviously, other choices could have been made, but I hope to have given you a good impression of the wide applicability range of ellipsometry in thin layer characterization. To wrap up, I would like to go through the strengths and limitations of ellipsometry. I've shown that ellipsometry is a non-contact, non-destructive technique for measurement of thin film optical properties. Because ratios are measured, the psi and delta that we talked so much about, the measurement results are not affected by intensity stabilities of the source or by atmospheric absorption. Ellipsometry is a very sensitive and precise technique that has submonolayer detection limits for surface concentrations. It can be used in a mapping mode to investigate lateral differences in layer property. Also, ellipsometry is unique in its capability with respect to the determinations of optical and other thin film properties. Obviously, the technique also has limitations. It requires optically flat sample surfaces. Ellipsometry does not provide compositional information, and complementary surface analytical techniques are required to measure those if necessary. Ellipsometry does not measure the optical and other material properties directly. An optical model must be fitted to the data. In some cases, this can lead to systematic errors, and again, other surface analytical techniques are required to check the accuracy of the result. As a final limitation, I would like to mention that with the present instrument, our lateral resolution is limited to 100 to 200 micrometers, although focusing optics with small spot sizes of several tens of micrometers are available in the market. As I mentioned earlier, at Eurofins EAG, we have a wide variety of different techniques at our disposal. The smart chart can be used as a guide to compare analytical techniques to determine which one is the best applicable to the problem at hand. But also worth pointing out that since no analytical technique can serve as an all-purpose solution, we find many situations where multiple techniques are necessary to solve the problem. As ellipsometry does not provide elemental information, we do require other techniques, such as those in yellow and orange here, SEM-EDX, XPS, or XRF for elemental information, or FTIR, Raman for molecular information on the layers to be analyzed. As I have shown in the examples presented, we also used XRR and AFM to measure layer thicknesses for absorbing films, where it proved difficult to determine optical constants and thickness simultaneously. Over the next several weeks, the Smart Charts webinar series will explore more of our techniques and will show how these complementary techniques provide a synergy to solve your analytical problems. So why choose EAG? Well, there are several reasons, but I think that it's important to state right at the top that client confidentiality is at the core of our business. Also, we are global leaders for materials testing services with a broad range of instruments and expertise that allows us to take on even the most challenging materials and engineering related issues. Finally, I'd like to make a couple of points in the light of the pandemic that is affecting us all right now. I want to stress that EAG Laboratories is committed to the safety of our staff and our clients. Worldwide, we comply with the latest COVID-19 regulations from the relevant regulatory bodies. Currently, all our locations throughout the world remain open, but we may have limitations on customer visits. As we are operating some of our labs at reduced capacity. We can also transfer samples to other EAG locations if needed. And we encourage you to talk to our sales representatives or technical staff to discuss your options.